Welcome to the second lesson dealing with absolute value and the absolute value of functions. In the first lesson, we looked at how absolute values uh, can be calculated, how you figure them out, what they mean, and what the graphs of an absolute value function of a line, say, looks like compared to the original line. So if you can imagine, we've been doing this for the past 4, 5, 6 years, right? We introduce one topic and then a little bit later we bump it up a notch. So here we're going to bump it up a notch by looking at the absolute value of quadratic functions. And then we're going to graph them and see what they look like. So hang on, fasten your seatbelts. Let's begin with a bit of a warm-up. We're going to do something easy peasy here. We're going to sketch the graph as a start. Sketch the graph of y equals absolute value of minus 3/5 x plus 3. So let's just remind ourselves very, very quickly what it is we're doing here. What we're doing is on an xy coordinate, we are taking a line, and this has a negative slope, so let's do a line with a negative slope, right? And what we're going to do now is when we take the absolute value of it, we're going to notice where that line crosses the x-axis, and we're going to start mirroring everything you see under the x-axis to the top. So it's that mirroring effect, which is what an absolute value, I guess it's a function, does to an equation or another function. All right. So when push comes to shove, we should have something that looks like this. Okay. But to get started, it's often a good idea, and I'd like to get started this way, even though it's a step you'll skip as you get more comfortable with this. What I'm going to do is draw the original line, which is going to look like this. I'm going to get you to draw the original line first. And then afterwards, we'll do some identifying of what's happening, and then we will then identify the absolute value of that line. All right? Ready? Let's go. So how do we get started here? We have a lot of information to get started with. And to get started, we're going to consider not the line of the absolute value of this function, but simply y equals negative 3/5 x plus 3. Because we can suss out a lot of information out of here, okay? So remembering the slope-intercept form of a line, we know that there is a y-intercept at plus 3. In other words, at 0, 3, that's where the graph crosses the y-intercept. And what else do we know? We know that there is a slope of negative 3/5. And with those two bits of information, we are ready to graph this line pretty much directly. Remember, we're going to start by graphing this line here, and then we'll figure out what the absolute value of that line is going to look like, what the graph of the absolute value. So here is the graph, and if you recall, we had a y-intercept of plus 3. So there we are. And we have a slope of negative 3/5, which means that the line goes down like that, not like that. Okay? So just so we're oriented the right way. And we're going to figure it out precisely by counting down 1, 2, 3. That's the rise. And over to the right by 1, 2, 3, 4, 5. And this point right here, which is also a lattice point, is going to be a point on the line. Gives us the x-intercept too, incidentally, which we will need to actually finish off this question. And similarly, if we go to the right 5 and down 3, we can go to the left 5, 1, 2, 3, 4, 5, and up 3, 1, 2, 3, and we can catch us another point on the line, just like that. And so now we're ready to join these points to see what this shape of this line is going to look like. And it's going to look like that in my best freehand drawn line. Now, hey, here's the thing. When you're working on a quiz or a test or an assignment or homework, use a straight edge. You always will have a straight edge at your disposal. What you want to, even if you have to use the edge of your ruler, use a straight edge. All right, so let's pick another color. Let's pick green now. And Because now this is y equals negative 3/5 x plus 3, because we want the graph of the absolute value of that line, then we're going to have to identify a couple things. First of all, we're going to identify the tipping point, I call it, or the point at which all of the y values become reflected about the x axis. Everything to the left of this graph is going to be fine. Everything to the left of this graph is part of the absolute value. So let me just choose a thicker line. Up to and including x equals 5. But going past that now, what we need to do is try to figure out where what shape the line is now. Now, we can't really do that because if I want to go with a rise of 1, 2, 3 and over 1, 2, 3, 4, you see I run out of room. So it's entirely okay to simply estimate. So I'm going to take this point at 4. I have no idea what that y value is, but I know that it very roughly corresponds to that. And that's all the information we're going to need to know to finish off this graph here. There we go. The question asks us to sketch the graph of the absolute value of that line, and in green is what I have. So here is, if I want to just label this, here is f of x. Cool. All right then. This should become fairly routine and fairly easy the more you practice it. Another thing that should now become more easy and more routine, because you've practiced it lots, is converting a quadratic from standard form to vertex form. So why in the heck should you want to convert a quadratic from standard form to vertex form? Because when you do that, you are able now to get some information that allows you to graph it. And that's what this lesson is all about. It's about graphing the absolute values of quadratic functions. And before you are able to graph the absolute value of a quadratic, you better darn well be able to remember how to graph the quadratic in the beginning, right? So we'll complete the square to convert this from standard to vertex form. And if you recall, there's a number of steps for completing the square. Step number 1 is to pull out, divide by the x squared coefficient, and see what you have. So if I pull out 3 out of 3x squared, I'm going to be left with x squared, and I'm going to pull out the 3 from the x part, and then I'm going to draw a bracket. I'm going to close my bracket around the x's because I'm done with it. 7 remains untouched. Okay. Next step is to take that x coefficient of 4, half it, and then square it. Well, 4 divided by 2 is 2. 2 squared is 4. And so we're going to add that into the mix. This is what's going to give us a perfect square. But if you're going to add 4, you got to remember to subtract 4. You just can't go around adding numbers in to make your equations look pretty without paying the piper. And paying the piper means subtracting 4 right away and keeping it inside the brackets. And again, nothing's happening to the 7. All right, next step. Well, let's pull the 4 out of the brackets. Okay, so we're going to get y equals 3 x squared plus 4x plus 4. And now we're going to pull the negative 4 out of the brackets, and we're going to do that by multiplying by the coefficient in front of the bracket, 3. 3 times negative 4 is going to be negative 12. And then don't forget the negative 7. Cool. All right. Well, let's finish this off. I think we can do it in the next step here. 3 stays outside. X squared plus 4x plus 4 becomes x plus 2 quantity squared. There is the square of completing the square. We've made it a perfect square. And in the end here, we're going to get minus 19. Cool. So why are we doing this? Because it gives us information. It tells us that we have a stretch factor of 3 times in the y direction. That is going to be pulled up. Okay, and that's useful to know. And it also tells us what the vertex is. Remember, you're able to read the vertex more or less directly off. You just have to change the sign of the x. So vertex will be -2, comma, -19. All right, so if I were to graph this very quickly, if I just want to do a sketch, before we go to the sketch on the right, what's this going to look like? It's got a vertex of -2, -19, so down here, okay, there's the vertex. And I mean, I'm not going to figure out what the x, well, we can figure out what the x-intercepts are, right? But we don't need to. It's going to, all I want you to know is that the parabola is going to look something like that, okay? It's going to have a couple of real roots, zeros, which has to do with the x plus 2 quantity squared minus 19, so we can figure out what those are if we wanted to. We don't have to in this question, but we could. But we get the general sense of the form of this quadratic fairly easily, okay? And I think that's all it asks us to do. We are done. Done like dinner, boom. All right, are you ready to move on and do some absolute values of quadratics now? Cool. So we're being asked to consider the function f of x equals x squared minus 4x minus 5. We want to sketch it. We want to determine the intercepts in the vertex. We want a full-on sketch, a good, accurate drawing of what this thing looks like. State the domain of range, and then we're going to figure out a sketch of what its absolute value looks like. And I think that once we get this thing drawn properly, that is before the absolute value function kicks in, I think it'll make a lot of sense about what's going to happen and what values are going to change. So we have a quadratic in standard form. I think the first step we should do is to complete the square and get some information that would allow us to graph it. So we're given f of x equals x squared minus 4x minus 5, and we're going to start completing the square. So first step would be to isolate the x squared coefficients. There are none, so we can simply go to the step where we draw brackets around the x's, the x squared and the x's, and we add in some kind of value that would allow us to complete this square. Minus 4x. Take minus 4 divided by 2 minus 2 squared, and you get plus 4. And when you add 4, you also have to subtract 4 and carry down the 5. Cool. And let's finish this off. I think x squared minus 4x plus 4 is going to become x minus 2 quantity squared minus 9. And what information do we have here to help us draw this thing? We know that the vertex is going to be at 2 comma -9. We know from the original form of the equation, looking back up here, well, right there, you might recall that information in general form, that last constant term, talks to the y-intercept. So we know the y-intercept is going to be at 0 comma -5. We know that much. Cool. And finally, the x-intercepts. Well, to get the x-intercepts, what we're going to have to do is go back to the x squared minus 4x minus 5 version and see if we can factor it. And if not, then we're going to have to do some quadratic formula magic on it or something. So we're going to take then, to find the x-intercepts, x squared minus 4x minus 5, make y equal 0, right? So it's going to be all equal to 0. And are there a couple numbers that work here? Minus 5. Oh, sure there is. It's going to be, what, x minus 5 times x plus 1. I think that will do it. X squared minus x plus x minus 5x. There's minus 4x. Minus 5, and yep, we are good. So this is good. So what does this mean? This means that x-intercepts, or the 0 is going to happen when x equals positive 5 or negative 1. Boom. So our x-intercepts, therefore, are and let's do them in the proper order. -1, comma 0, and 5, comma 0. So all of a sudden we have more than enough information to graph this guy. Let's go back to the graph now and zoom in, and let's see if we can't fill in some blanks here. Okay. So first off, the vertex at -2 or at +2 -9, which will be here. And let's do this. Let's keep this in green because that was the original. Okay, so there's the vertex. We know we have a y-intercept at 0, comma -5. So there's the y-intercept. Because of symmetry, we know that if 0, -5 is a point on the parabola, that 4, comma -5 is also a point on the parabola. Cool. And we know that this is what we call a regular parabola with no coefficient in front of the x squared. So we know it goes over 1 and up 1, over 2 and up 4, good, and over 3 and up 9, which is there. And luckily, that also gives us what we know to be our x-intercept. And we can work the other way as well. Over 1, up 1, there, good. Over 2, up 2 is good. And then over 3, up 3 brings us to -1, comma 0. And yay, that's our other x-intercept. And I mean, you can go further. You can go over 4 and up 16 if you want. But let's do that. Over 4 and up 16. We're already up 9. 1, 2, 3, 4, 5 more should do it, right? No, 6 more. 7 and 9 will give us the 16. And what am I doing there? Well, because it's x squared, means that for every one space over, it goes up by however this is squared. So if we're going over 4, we're going to be going up 4 squared, or 16. And there we are. Cool. Now it just relies on us to, well, we can do this line from symmetry. And now we just rely on trying to draw this parabola as neatly as we can. And that is not too terrible. That is not too terrible at all. All right. So let's go back and see what we're being asked to do here. We have to sketch the graph and determine the intercepts in the vertex. I believe we have done that. We have the x-intercept. We have we have the y-intercept, we have the 2 x-intercepts, and we have the vertex. We are good to go. And if you really want to be really keen, you can go in there and label these points. I just want to do this. I want to label this curve as f of x. That's f of x. All right. And now I'll state the domain and range. Let's do that. Let's state the domain and range of f of x. Well, for parabolas, the domain is unbounded. It goes forever in the negative direction and forever in the y direction. So let's use interval notation. The domain are all values of x from -infinity to +infinity. And for the range, recall, for the range, we have to look at what the vertex is, because the range is everything from here up, okay? And so the range now is going to be -9 is the lower bound, and because we include -9 in the range, we have to draw the square bracket, comma, and then now +infinity in the upswing, and there is our domain and range statement for f of x. Cool. Now, to do the next step, which is to figure out what the graph of the absolute value of the quadratic looks like, we have to dig deep a little bit and think deeply about the simple idea of what an absolute value function does to any other function. What it does is it takes any y values that are less than 0 and it reflects them about the x-axis. So any part of this curve which is currently above 2 or equal to y equals 0 is going to be part of the absolute value function. This part of the graph here is part of the absolute value function of the original function, and that part there is. And now the question is, how do we resolve what is left in green? Well, the idea is that absolute value takes those y values and it flips them. And what does that mean? It means that instead of 2 comma negative 9 for a vertex, it's going to flip it up to 2 comma positive 9. I'm just going to zoom down. I'll scroll down a little bit to right there. Okay. And everything else about the graph is going to be a nice mirror image. Now, you know how we went from this point, left 1 up 1, so left 1 up 1 squared, or right 1 up 1 squared. Oops, I didn't do that right. That should have been there. Okay, so we can do the same thing here. From the vertex, we're going to go right 1 and down 1 squared, left 1 and down 1 squared. We're going to go right 2 and down 2 squared, or 4. Down over 2 and down 2 squared, or 4. And that's going to probably give us enough stuff to work with. The absolute value function now can be drawn in. You've got the bits that we need. And then finally, it probably behooves us to label in purple. This is g of x, where g of x equals the absolute value of f of x. Cool. All right. So I think we have knocked off another one of our list of to-dos on this question. Sketch the graph using the graph of f of x. Okay. Boom. We have done that. And now express the piecewise function and state the domain and range of g of x. All right. So the piecewise function, there's going to be two parts of it, just like there were two parts in the line. Instead of one tipping point or one important point of the x-intercept for a straight line, there's now 2 points. So we're going to have to define what this part of the graph is, that is between -1 and 5. And then we're going to have to define this part of the graph, which is both less than -1 for x equals -1 and greater than x equals +5. For g of x, all right, the domain is going to remain unchanged. So here's something you can file in the back of the recesses of your gray matter. When you do absolute value, the domains of functions don't change. So the domain is going to remain from -infinity to +infinity. That's easy. Now, the range, however, is going to be different. There's going to be two.
Oh, hey guys. All right, I got done messed up. So what you're about to see is that the range of the absolute function transformation of an original function is indeed different, but it's not what you're about to see. You see what I did there? You see, what happened is I got my head thinking about some stuff from Math 30-1, where when you get a really complicated function on an XY graph, it might go, goes really weird. You do actually break down the range for different parts of the graph, and that's what I was going on about. So ignore what you see next to the range. The range is actually pretty simple. The range does change, just not dramatically. Instead of from the minimum underneath, the range now, the minimum y value is going to be at the y equals 0, in other words, the x-axis. And it'll go from y equals 0 on the left side, at the bottom on the left side of the expression, all the way up to infinity. So it does change a little bit, just not the way you're about to see. What you're going to see that is improperly labeled as range r is the piecewise function of the absolute value transformation of the original function. So disregard the labeling. The range is going to be from 0, including 0, so I don't know, square brackets. And on my screen, everything is reversed, so this should be on the left side. Okay, so from 0, including 0, to +infinity. Now back to regularly scheduled programming. Ah, but wait, I've got a treat for you. Since you've come so far with me and stuck with me because I've messed up, I have an introduction to make. This is our new Siberian mountain cat. This is Callisto Canopa cat. She is brand new to us. We've had her just for a couple days. She is 13 weeks old, and she is just a little fur ball. Look at her tail. And she sleeps through all of this abuse. Anyhow, meet Callisto Canopa cat. Now we'll get you back to regularly scheduled programming. Cheers.
Different. There's going to be two statements of range. See, on the left side of x equals -1 and on the right side of x equals 5, the range doesn't change. All right? So for the range, there's going to be two parts. Okay? There's going to be a part of the range for which x is less than or equal to -1 and greater than or equal to 5. We have to define that part of the range. But now there's also going to be a part of the range inside, in between -1 and +5. And so that's going to be -1 less than x less than 5. For the part of the graph that is for x less than -1 and greater than or equal to -5, less than or equal to -1, the function remains unchanged. So it's simply x squared minus 4x minus 5. That defines the line of the former parabola for x values less than -1 and for x values greater than 5. For the interval between -1 and -5, what we're going to do is take the inverse, or the reciprocal, of x squared minus 4x minus 5. And what that's going to be is -x squared plus 4x plus 5. Okay? And take a moment there and see what we did to get the reciprocal. We simply changed the signs on every part of the function. X squared becomes -x squared. -4x becomes positive 4x. And -5 becomes positive 5. Boom. We got it. This is all you need to do. It's not that hard once you get your head around a couple of things. All right. And then the last thing is that we have still that idea of invariant points. The part of the graph that doesn't change is invariant. So all of these points here are invariant points. And everything over here are also invariant points. Now it'd be nice if we had a name for the points that did get flipped. I guess we're going to call those variant points. They vary. But in orange are the invariant points, just like a line. I think we're ready to move on for another example. All right, so let's do the one last question. Let's turn the page on page 174 and tackle question number 2. It looks very similar to question number 1. Should not be a problem. We're asked to graph the function of y equals the absolute value of -2x squared plus 12x minus 10. And to do that, we're going to try to figure out the, well, we'll put it into vertex form so we get a vertex and we get an idea of the stretch and the orientation, whether it opens up or opens down. We'll figure out some y-intercepts straight away, and then we'll determine the roots of this equation, which will yield the x-intercepts. And with all that information, we will be golden. I'm going to start with the y-intercept. Now, normally, if this was a parabola of y equals -2x squared minus 12x minus 10, then we would just pull off that last term there and read it off, and that would be the y value for the y-intercept, 0, -10. But this is an absolute value function. And so, I mean, you do it the same way, and we're going to end up with a slightly different intercept. So you know that this parabola opens downwards. That's what the negative 2 tells you. Well, that's what the negative tells you. And it's got a vertical stretch of 2. That's what the 2 tells you. So just with my experience, I know that the absolute value is going to change the y-intercept from negative 10 to positive 10. But how would you know that if you didn't know already to recognize that you have to take the absolute value of negative 10 to find the y-intercept? Well, y-intercept when x equals 0, right? So y is going to be equal to absolute value of negative 2 times 0 quantity squared plus 12 times 0 minus 10. All right. And all of this mess here is just going to be 0. So we're left with y equals the absolute value of negative 10, which equals 10. Remember that the absolute value of a number is neither positive nor negative. It's just a distance. It just is. So the y value for the y-intercept now, as we surmise, because we're taking the absolute value, is going to be on the other side of 0 from negative 10. And so the coordinates of that y value of that y-intercept are going to be 0, 10, just like that. All right, so what else can we do? Well, we're going to have to determine the x-intercepts as well. And when you get the x-intercepts, you get the x-intercepts when y equals 0, when y equals 0. So when the absolute value of negative 2x squared plus 12x minus 10 equals 0, you should be able to find the x-intercept. All right, so let's take the absolute value signs away. And, well, in fact, we don't know the values, the final values of what these numbers are going to be. And so you can pretty much ignore the absolute value sign in this case. Even if we were concerned with how the absolute values of this whole expression here would affect it, we know that the zeros or the x-intercepts of a function are the same as the zeros or the x-intercept of its absolute value. So we can just ignore the effect of the absolute value signs here because they'll have no effect on anything. All right, so how are we going to deal with this? Well, we can probably, looks like we might be able to factor, but we can also, and why not, right? Let's take negative 2 out because I think that's going to look a little bit nicer. Yep, it sure will. We're going to get negative 2, and the two roots of that, I think, negative 5 and negative 1 work. Let's see, x minus 5 and x minus 1. X squared minus x minus 5x. There's the minus 6x, and then plus 5. Good, that does work. And so now we know that the x-intercepts happen at x equals 1 and 5, and that the x-intercepts themselves, therefore, are 1, 0 and 5, 0, just like that. Do we have enough information to solve yet? Nope. I think now what we're going to have to do, well, let's get some points down here. We've got 1, 0 here, and we've got 5, 0 here, and we've got 10, which is way up here. I think 10 will be right there. But that's not yet enough information to be able to graph it. We'd like to know where the vertex is. So let's complete the square of this mess and see what we get. Okay, so we're going to zoom in here. To complete the square, we're going to take y equals the absolute value of negative 2x plus 12x minus 10. All right. And so the first step is to try to get rid of that x squared coefficient. So we're going to pull negative 2 out, and we're going to be left with positive x squared minus 6x. Close the parentheses for now, and then we're going to keep the minus 10 outside like that. Next step is to take the x term, the x coefficient, which is 6, half it, and square it, and add it back into the mix. And there it is. And when we add it, we're also going to have to immediately subtract it, otherwise we change how this quadratic will look. Close the brackets, minus 10. So negative 2, it's a downward opening parabola with a vertical stretch of 2. X squared minus 6x plus 9 is going to be brought down to its perfect square of x minus 3 quantity squared. Okay, that's going to take care of that part. And then we're going to take the negative 9 out. Negative 9 times negative 2 will be plus 18. And don't forget that we still have the minus 10. Cool. And then finally, negative 2 times x minus 3 quantity squared plus 8. There we go. So there we have completed the square. And all of a sudden, we know that the vertex is going to be at 3, 8. Okay. All right, so let's graph this. And in the same way that I drew when we were working with straight lines, y equals mx plus b, I drew the original function first, and then I drew the function of the absolute value of the original, because I wanted you to see how one is related to the other. So likewise over here, I'm going to draw the original parabola first, and I'll do that in light blue. And we know it's going to look like something like that, right? Exactly what? Well, let's figure it out. And so if it does look like this eventually, it's this part here that's going to get reflected up. So it's going to go something like that, we think, okay? And I want you to see and be able to understand the relationship between the absolute value of a function and the original function. So let's get rid of all this and let's do this properly, shall we? All right, so what do we know? We know that the vertex is at 3, 8, and that is a true vertex because it's above the y equals 0. So 3, 8 puts us right around here. Good. And what else do we know? We know that there are x-intercepts at 1, 0 and 5, 0. So 1, 0, there's one x-intercept, and 5, 0. And it'd be nice if these were symmetrical about the vertex, the line of evil symmetry. And in fact, it is 2 over there, 2 over there. Good. And finally, we did learn what the y-intercept of the absolute value was. It's 10. But we're going to do the y-intercept of the original function, which when you're looking at this, if you ignore the absolute values, we get minus 2x squared plus 12x minus 10. The y-intercept would be negative 10. So I'm going to draw the original f of x, and then we will do the absolute value of f of x. So negative 10, 0 would be down here, okay? Now, because of symmetry, this line here is 1, 2, 3 spaces from the vertex, the axis of evil symmetry, and so 1, 2, 3 more over should be good as well. And because this is a parabola with a 2 times vertical stretch, we can try to estimate a point 1 over. Now, normally with a parabola, if you go 1 over, you go 1 squared, either up or down. But if this is a 2 times vertical stretch, we're going to go 1 over and 2 times 1 squared, or 2 down, and down over here because of symmetry. See how that works? With just an x squared parabola would be over 1, up 1, over 2, up 4, and so on, or down 4, or down 2, right? But with a 2x squared parabola, it's going to be over 1, down 2 times 1 squared, over 2, down 2 times 2 squared, or 8. 1, 2, 3, 4, 5, 6, 7, 8. And look at that, we establish our x-intercepts once again. And going the other way, over 2, down 2 times 2 squared. 2 squared is 4, another 2 squared will give us there. Good. So that confirmed the x-intercepts correct. And now we can simply draw as best we can a fair representation of what that parabola looks like. Now, unfortunately, the question is not asking us to graph the function minus 2x squared plus 12x minus 10. It is asking us to graph the absolute value function of that parabola. And so remember that little drawing I did before? It's gonna I said it's gonna look like this, and then these ones are gonna come up like that. So how does that work? Well, I'm gonna draw the absolute value function in a nice funky nifty color there, and I'm gonna zoom in a little bit. All of the y values that are above y equals 0 are going to remain the same. So that part of the parabola is part of the, do we call it g of x? No, we just call. So here, I mean, here, if this is, if f of x equals negative 2x squared plus 12x minus 10, then the absolute value of f of x is, well, we're just going to call it g of x, just to put it in, okay? So this is g of x, which it happens to be the absolute value of f of x. Cool. Now, what is going to happen now is to figure out what to do with these blue tails. The blue is f of x. We want to convert them. They are just flipped about the x-axis. So if this is 6 comma negative 10, a vertical reflection is going to bring it to 6 comma positive 10. And likewise, 0 comma negative 10 is going to be 0 comma plus 10. So that's where it's going to go. And now the rest of the curve can be sketched thusly. There we go. That kind of looks like what I promised it would look like. All right. Graph the function of the absolute value. So there's g of x. We've graphed that with your calculator. Write it as a piecewise. So all of this stuff here, and to a certain extent, this stuff here was in service of our being able to graph the original parabola. Once you have the original parabola, you can then do your mirror images of the points that are below the x-axis, below y equals 0, and then you can sketch its absolute function shape. The last thing we're always going to want to do now is to state the piecewise functions. All right, the piecewise functions. Peace be with you. Because the piecewise functions are going to be divided into two parts. Let me choose some nifty colors here, and let me go ahead. So there's the part of the graph then that is inside the boundaries, the axes, and these are going to be the original function, and then there's going to be that area on both sides, which are going to be the transformed function, the absolute value function. Abs value, abs value. Okay, and so how do we state that? Well, it's easy to figure out the middle one because it's unchanged from the original function. So let's do the piecewise function here. Okay, there's going to be two parts. Now we'll formally define how to state it. Y is equal to, and there's going to be two parts. Okay, when x is greater than or equal to 1 or less than or equal to 5, and that corresponds to this area here, okay, that area there. When x is greater than 1, greater than or equal to 1, and less than or equal to 5, then the equation of the absolute value of the function is the original function, minus 2x squared plus 12x minus 10. But when x is less than 1 or when x is greater than 5, the equation of the function for this is going to be the reciprocal of what you saw there. And how do you get the reciprocal? You change all the signs. So it'll be 2x squared minus 12x plus 10. There we go. That, I believe, completes everything we're being asked to do. This piecewise function, because for the absolute value, the three parts of the curve are defined slightly differently. All those parts that are normally and originally above the x-axis will remain unchanged, but those parts that dipped below the x-axis will get reflected upwards. And remember now that invariant points are all around us. Let's choose a color we haven't used yet. Let's choose brown. Okay. this part of the graph here is invariant. They don't change. And the two most important invariant points, the two most important points that do not change are going to be those x-intercepts. So let's go down to the bottom here and let's see if we can get a little bit of summary, see what the summary and review means. Remember that when you're taking the absolute value of a function, it's only the y values that are affected. Only the y values. And not only that, it's only the y values that are below the x-axis. So all the y values less than 0. The two most important invariant points are the x-intercepts. And steps for graphing, well, graph the original function. That's what I like to do. Graph the original function, label the x-intercepts in the vertex, and then change any negative y values on the graph. Just do their mirror image on top of the x-axis. And you will be done. All right, carry forth. Page 175 begins your practice questions. Happy mathing. Peace out.